All right, let's bring it all together with the candidates test. So this is how we can use that extreme value theorem to actually find those extreme values. First, we need to figure out our critical values. Still important because where we have a local max, it could end up being our absolute max as well. Then we're going to make a table of values. What do we mean? We need to include both the critical values because those are possible ones, right? I'm going to use my green because I've been using green for critical values. But we also need to include our endpoints, right? We're on a closed interval, and in a lot of our examples that we've seen so far, the endpoint ended up being one of our global extrema. So we need to create a table using those. When we're finding these absolute extrema, we're then just going to plug these into the original function. This is the most annoying part of this candidates test is that we have to go evaluate our function multiple times. Okay, so we're going to plug these into and let's just write original function, the OG. We need to make sure that we're doing that because otherwise, right, if we're in critical value land, we have our derivative, and so we're kind of done with the derivative at this point. All we wanted was critical values. Now, we could be smarter about this, and we could even think about when our first derivative changes signs, because if it doesn't change signs, it's really not a candidate, and we'd at least have one less thing to plug in. It kind of depends on whether we have the computational power of being able to plug into something like Desmos or a calculator versus if we don't have that ability, right? It depends how gnarly the evaluation is. Um, and then it's as simple as looking for the biggest and the smallest thing. That's it. Now, we do have a nice sentence here about how to say these. We are going to say our global maximum or absolute maximum is give the y value, right? In fact, maybe let's not even write that as y. Let's be like, ooh, f of c at x is equal to c, right? Is this value at the x value? So it's always going to be about our y because that is the maximum. And then we might have some, I'll use a different letter, f of k at x is equal to k, right? So y is y at our x. Cool. There are a lot of ways this can get asked for that you need to be paying attention to. Oh, that's not what I wanted. I wanted to bring over that cute little, what is that called? Like dialogue box. Hold on, I'll bring her. All right, boom, there she is. If we're asked for an absolute or global, right, those are two words, but even just not having that language implies absolute or global, right? Local is a very specific thing. If I say what's the maximum value of a function, it does mean global or absolute. All right, let's go ahead and look at a couple of graphs and see how these work out for us. So first thing we're going to do, we're going to check our two conditions for the EVT. We need to make sure that we can even do something, right? So is it continuous? Yes, look, beautiful, continuous. Yes. Is it closed? Well, bloop, bloop. Solid points on the ends, so the answer here is yes. Which makes the next question also yes, right? Those are the conditions needed for the EVT. Cool. Now we can ask, okay, well, does it have well, yes, right? These all follow from each other. The EVT tells me if those two things are met, then it's guaranteed to have a max and a min. All right, so then we could write those down following that sentence from before. The absolute maximum is. So here we would say the absolute maximum is, and the highest up this little function ever gets is right there as 3 at x is equal to -1, and the absolute minimum is whoop, way over here, -1 at x is equal to -3. Cute. All right, let's keep going. Let's do the next graph. So continuous, whoop, closed. Wah, 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 wah. No, this is not closed. It doesn't have our filled in circles at the ends. So we cannot apply the EVT, and it doesn't have a max or min. Well, doesn't have a max, right? But can't apply that. No, does have a min. All right, so we could at least make that statement. Our minimum value happens here. The maximum we never will reach. It goes really, really close to that open circle, but never gets there. The absolute min is -3 at x is equal to -1. Now, just because it doesn't have the EBT doesn't mean it can't have an absolute max or min. Just means it's not guaranteed to have an absolute max or min. All right, so we have one more. This beautiful but hideous graph, right? It's chunky. She ain't differentiable because it's not smooth, but it is continuous. And we see it is closed. So we have 3 yeses in a row, right? Yes, it's continuous on a closed interval. Yes, I can use the EBT. And yes, I am guaranteed to have an absolute maximum and an absolute minimum. Boom, boom, yes. Now, if we look at our actual curve here, it appears the maximum value, like I said, no guarantee it has to be unique. We have a maximum twice, same maximum. The absolute max, I'm going to move my face. That's not the problem, though. My pen wasn't working. The absolute max is 4 at x is equal to -3 and +3. Cute. So it just happens twice. That's okay. It's still the maximum value. And the absolute min, come on, is lowest point is there. 1 at x is equal to 1. All right. So let's go ahead and move on to looking at things that aren't graphical, right? Where we have to then know how to check those closed and continuous. It's not as bad as it seems, but then we'll have to actually do the candidates test and plug in values too. So let's move on and try that out with some of the examples in the lecture videos below.